Very good. Welcome everyone to the Solar Electric Investment Analysis web seminar series, part 2. This segment is on assessing system cost. As you recall, our first session was on estimating system production, and you can go back and view that in the link that we sent you. Also, at the end of all the sessions, we'll have all the videos available to be linked all in one place, but right now we're doing it one at a time because we're creating them one at a time. This web seminar is brought to you by the North Central Region SARE through some grant dollars that they have granted us to do some education for extension, USDA rural development, NRCS, rural bankers, and the goal of this is professional development for you so that you can have better conversations as well as maybe be able to do some of these analysis on your own with your clientele and hopefully improve their ability to make decisions related to these. So these sessions really are for you, obviously, and please ask questions as you have them in the chat box. I'm going to be managing the questions today. My name is John Hay. I'm with the University of Nebraska. I'm going to go through and manage the questions, and Eric Romick is going to be our presenter today. He is from Ohio State University and has quite a lot of experience working with, in particular, farm systems with solar, but also at other businesses, and has been doing this for a number of years. You should be seeing the slides. The slide that's up right now basically goes through all of the 6 parts that we're going to cover over the 6 sessions in these 3 weeks. We're on number 2, assessing system costs, but during parts 4 and 5, we're going to take a few minutes to talk about solar leasing issues. Part of that, we feel like that's become a hot topic, and we're getting more and more questions about that, and so we thought we'd share some of the insights that we have and some of the things we've learned related to giving advice to farmers about solar lease agreements for utility scale solar. In general, we are going to be covering distributed systems and smaller personally owned systems at farms is going to be our main audience, our main thing we're going to talk about. But this information also applies to other business systems and could even apply to residential systems. The knowledge could be applied to that. But we're going to use everything in terms of farm systems for this series. So with that, I'm going to turn it over to Eric for today's presentation.
Great, thanks, John. As mentioned, this is the second session of our 6-part webinar series, and we're focused today on assessing system cost. And when you think about the topic system cost, it might seem like it's a little bit of a topic that there's not a lot of content there. So what are we really talking about when we think about system cost? And it's kind of interesting when I think back to some of the discussions I've had with farmers who are considering proposals or reviewing proposals. I might ask them what appears to be somewhat of a simple question, and that is, what are you paying for and how much is it? And that seems like a question that should be fairly easy to answer, but you'd be surprised at when you stop to think about it, how difficult that may be. Oftentimes when we're looking at some of the materials that are shared with farmers or businesses, they tend to speak in terms of payback period. We see a lot of system costs that reflect a quote-unquote net system cost that is kind of a perspective after the tax credits, depreciation, renewable energy credits, other incentives like that are monetized, which can be a bit misleading at times. So, if we think back to John's talk on Tuesday, related to how systems are designed, the equipment and components that are used, and how that all impacts system production, I think it's important to make sure that we can answer the simple question, what are you paying for and how much is it? And so as we go through today's talk, we're really going to try and break this down to kind of take a look at the historical price trends of PV solar. We're going to kind of itemize some of those costs. So we'll look at equipment cost, soft cost, and some of the kind of quote unquote other and ongoing costs that you may occur through this process. And then we're going to kind of take a brief moment to look at the influence of energy, or I should say improved panel efficiency and power output. And then we'll summarize with some lessons learned and provide some additional resources. Provided we have time, we'll open up the system advisor model and possibly introduce you to that tool as well. So, kind of jumping into this, we're going to start by looking at a high level, kind of the price trends of photovoltaic or PV solar. And this is a chart that is based on data that's put out quarterly by the National Renewable Energy Laboratory through DOE that looks at the benchmark pricing for PV solar nationally. And they have this data for different types of systems. So they have this data for residential systems, commercial systems, and utility scale systems. But you'll notice with the data we're looking at, we're looking primarily at commercial systems, which for the most part, I kind of look at a commercial system as anything larger than 10 kilowatt, but anything maybe smaller than, say, a 200 kW system. So, as the chart illustrates here, you can see we've seen significant decrease in the overall installation cost from 2010 to 2018, and total a 66% reduction. Now, right around 82% of that reduction can be directly attributed to reductions in equipment cost, and we'll dive into that a little bit more over the next few slides. But I'd like to just kind of take a moment and absorb this 2010 number of $5.43 versus 2018's $1.83. And what I'd like to do is kind of compare that benchmark pricing from DOE at the national level to kind of an unintended case study that I've experienced here in Ohio. And what I mean by that is these are two systems that, just kind of through dumb luck, are located in the same county, on the same utility line. So same county, same utility provider. They were installed by the same installer. So the only real difference that we're experiencing here is time. And you can see that in 2010, we were at $5.98 per DC watt. And in 2016, we're down here at $1.85 per DC watt. So, it's kind of amazing when you think about how accurate the NREL modeling is as it relates to commercial pricing. It's fairly, we were off by 3 cents compared to what we saw here in 2016. So one of the other things that's kind of interesting on this slide that you may notice is while the costs have dropped significantly, as we look at the actual payback period, you might notice that we've seen a reduction in the payback period an increase from 3 years to 7.5 to 9 years. And the reason for that is, while the system costs have been coming down, we've also seen a reduction in some of the value of some of the incentives. So as an example, in Ohio, our renewable energy credits were significantly higher valued in 2010 compared to 2016. And that's a topic that we're going to dive into a little bit more during session 4. But just note that that's the reason why we're seeing that increase. Even though we see a decrease in the prices, we're seeing an increase in the payback period. And also just to kind of put a plug out there for session 5, we're going to talk in session 5 why payback period may be kind of a simple and somewhat useful metric. It's certainly not the best metric to be evaluating these projects with. So we'll talk about that a little bit more as well. Oops. So a real quick poll question before we dive into this. I'm going to open the poll, and I want to see kind of what your initial thoughts are on what category makes up the greatest portion of the overall installation cost. So, think back to the 2018 cost. It's $1.83 per DC watt to install these systems. What makes up the greatest portion of that? Is it this the modules, the inverters, balance of systems, which would include all of your racking and electrical components, the permitting, interconnection, overhead. We'll give just a few minutes for some of those results to roll in. And and while I'll share your initial results from this poll question, I'm not necessarily going to give you the answer up front. I'm going to make you listen to the next 5 or 6 slides, and I think we'll kind of answer this question together. Right now we got about 60% of the votes in. We'll give it just a couple more seconds. I'll close the polls in 3 seconds, and there we go. So can you see the results, John?
Yes, I can see the results on the screen that shows all the, I have mine set up as 2 screens, so I see the one with all the people, and it's on that screen.
Okay, great. So the most of us think that installation makes up the greatest portion of the installation cost. So we're going to kind of look at that here as we go forward. Now, we're going to start out by breaking down the equipment cost or hard cost, I guess we'd say. And we're going to start with, I guess, what tends to get the most interest. That is the panels themselves, or the modules. And so this chart is illustrating the price trends or the cost trends from 2010 to 2018 for the actual modules themselves. And you can see we've seen an 84% decrease in module price from $2.23 per DC watt in 2010 to 36 cents per DC watt in 2018. It's kind of interesting. In 2017, there was a lot of interest and a lot of people that were very concerned about the import tariffs on panels. And depending on what newspaper you picked up, it might sound like the sky was falling. I mean, there were people really concerned that this could just kind of devastate an industry. And you see that we have seen a little bit of an uptick in prices based on those import tariffs, but it certainly wasn't the doom and gloom that some feared it may be. And in fact, the module prices, that we experienced after the tariffs are still significantly less than what we experienced in 2016, which is a year when the U.S. Had record installations. I mean, that was kind of a record year. So not only did the industry prove that it could survive at higher price points, but also thrive. And then you'll see here we have, I'm going to kind of continue to share this $1.83 per DC watt. This was our total installation cost in 2018 for a commercial system. And you can see this 36 cents makes up about 20% of that total installation cost. Now, if we reflect back to 2010, modules accounted for right around 50% of the total installation cost. So kind of moving on to inverters, we see a very similar trend where we've experienced a 72% reduction in cost for inverters from 2010 to 2018. Now, traditionally, inverters have kind of always accounted for right around 6 to 7% of the total installation cost. Based on the 2018 cost, we're at 4% of the total installation cost is accounting towards the inverters. Now, John mentioned Tuesday about a number of different types of inverter technology, right? We have different options as we think about designing our systems that we could look at. And the picture here is showing a couple of SMA string inverters, 3-phase string inverters. And that's actually the cost that we're modeling here. So as you think about, how much we're accounting for the inverters, that's going to be dependent on the type of inverter technology you're using. So right now we're looking at, and I kind of want you to pay attention to this 2016 number of 12 cents per DC watt for the string inverter. That's what we're going to show in this chart here. So this chart is showing, and the most current data I had was 2016, but it's showing the variation of cost per DC watt for the different types of inverter technology. So this is the 3-phase string inverter, which we charted out on the previous slide. You can see single-phase string inverters a little bit more expensive, micro inverters significantly more expensive, and then of course our DC optimizers and a central inverter that would be used typically in a utility scale project. So when you look at this, you might ask yourself, well, why in the world would I want to use microinverters or DC optimizers to increase the cost of my project. And I think John did a really good job of illustrating how those technologies can increase the production of your system in certain applications, right? So John talked and illustrated the impacts of shading, for example, of a string inverter versus a microinverter or DC optimizers. The other reason that we want to possibly consider that would be, again, safety. And so as we look at Article 690.12 of the National Electric Code, it addresses rapid PV shutdown standards. And again, this is focusing on systems that would be located on rooftops. So if you have a system that's integrated into your building, that's where this safety code is mostly concerned, because what we want to do is minimize live DC wiring. Again, so I'm not a very good artist, but I'll just kind of attempt to try and make a point here. So this is a string inverter, a SMA string inverter. Again, this is going to be connected, so we'll have these wires that come over, and they're going to be connected to, you know, a large solar array here that is collecting sunlight and generating electricity. Now, if this string inverter loses AC feed, so let's just say on this building there's a fire and first responders show up and we kill the power, and this inverter loses AC line feed, it will effectively shut itself off. The problem and the concern with the rapid PV shutdown is, in this situation, if you have these panels on your rooftop, any of this DC wiring between your panels and your inverter, if those panels are exposed to light, will be energized. And that's the heart of this safety standard, and why you may spend more for a different type of inverter technology is microinverters. You can see here on the back of these panels, they actually do the DC to AC conversion right at the panel, right? Down here we have a SolarEdge inverter that's using DC optimizers. And what you'll notice, if I clear my drawings and shut that off, what you'll notice there is, if you really look at that label, it says this PV system is equipped with rapid PV shutdown. So long story short, you in some cases may need to spend a little bit more for certain components just simply to be in compliance with electric code. Okay, moving on. The last categories we look at equipment cost is what we refer to as the balance of systems, or sometimes you'll see that abbreviated as BOSS. And oftentimes this could be broken into two different categories, both structural, which would include your racking components. So think of your post, your racking material, the clips, the fasteners, the hardware, and then also electrical components, wiring, wire clips, combiner boxes, conduit, things of that nature. So for this slide, we've combined the two. And once again, a very similar trend where 2010 to 2018, we've seen roughly a 59% decrease in the cost for our balance of systems. Now, the balance of systems accounted for 14% of the overall installation cost for a commercial system in 2018. All right, so we're going to kind of take a little bit of a pivot here and start to talk about soft cost. And kind of at a high level, some of the things that we are talking about when we look at the soft cost of installing a commercial PV system on your farm or business is your installation and labor cost. What you might see is PII, permitting, inspection, and interconnection. Land acquisition, that's not quite as much for a commercial system. That would be more for a utility scale project. Sales tax, EPC, your engineering, procurement, and construction, and then just your overhead and net profit. So kind of broken these down into two categories to kind of evaluate. So we separated out the installation labor cost, whereas we're looking at roughly a 46% decrease. Historically, installation and labor has accounted for less than 10% of the overall cost. So while we've seen the actual cost allocations for installation labor go down, it's traditionally been about 10% of the overall installation cost, and you can see in 2018 we were right at 9%. And then our final category is PII, permitting, interconnection and inspections, engineering, procurement, construction. sales tax, overhead, net profit. And you can see this is, while we've seen reduction, it's not the dramatic downward trend that we've seen with a lot of the other categories. And this, I guess, shouldn't come as a surprise if you've been paying attention to our pie chart there as we've moved along. As the last category, it accounted for 50% in 2018 of the overall installation cost. And if you can kind of recall our labor here, our installation labor in this yellow triangle is 9%. So if we combine those, we're at basically 60%. Let's say 59% of the total installation cost in 2018 for a commercial system. So this red trend line is the portion of the total cost that's accounted for by soft cost for commercial systems, and we're 59%. So again, let's just say 60% of our total installation cost for a commercial system is soft cost. Again, that's not to say that there's certainly reason to monitor what's happening as it relates to equipment cost, but the savings that we've seen, so that massive reduction from, say, $5.43 per DC watt in 2010 to $1.83 per DC watt in 2018, the bulk of that reduction has been due to the reduction in the cost of equipment. I would expect maybe next year we see a little bit of an upward trend again, with panels possibly related to import tariffs. I would expect that we may see a little bit of an upward trend as well with the balance of systems when you think about the import tariffs on steel and aluminum at this point. So, but nonetheless, that's still, at the end of the day, 40% of the overall cost of the installation is due to equipment. So I want to kind of refocus now, or maybe hit the reset button, and we're going to look at some of these other costs. And these are costs that don't necessarily fit neatly into any one type of a category, but as you evaluate projects, one of the things that John and I try to look at is what are real costs, right? What are costs that you will pay in one way, shape, or form over the next 25 years that you install this? And we try to make sure that we're accounting for those in some way during our modeling. And so what I'd like to kind of look at is cost of capital. So if you're borrowing money for this project, you certainly need to account for the cost of capital, sales tax, property tax, insurance, and operations and maintenance. And we're going to look at a couple of these a little bit closer over the next few slides here. So 25 states, and this is as of a couple months ago, 25 states have had some type of an incentive program passed for sales tax exemptions. And 36 states plus DC and Puerto Rico have some type of a program for property tax incentives as it relates to renewable energy. This is a resource. If you haven't seen it yet, it's one that John and I will probably highlight several times throughout these series. It's the database of state incentive for renewable energy and efficiency programs. It's desireusa.org. It's a very up-to-date and comprehensive database as it relates to renewable energy policy and incentives. You can filter it by state. You can filter it by incentive type. A number of different ways to really understand what's happening specifically in your state. And the thing that I like is it links it back to the original code where those policies originated. So that's certainly a resource that I would encourage you to get familiar with if you haven't already in your state. So I want to look at an example as it relates to the impact of sales tax, and we're going to look at it from a couple different perspectives. Now, one of the things that we are fortunate here in Ohio is we do have an incentive for sales tax. Now, I want to put together just kind of this scenario. We're going to focus on a 50 kilowatt system. We're going to assume an installation cost of $1.85 per DC watt, and work from that to look at what the impact of sales tax would be. So in Michigan, they have at least, and then again, this was as of a couple months ago, so policy is fluid. These are subject to change. But Michigan had no sales tax incentive as it related to solar development. And so their sales tax was all at the state level. So at 6%, they were going to pay just over an additional $5,500 for that project. And if you add that and then break it down, we're basically increasing our $1.85 per DC watt to $1.96 per DC watt. Now, Ohio, we're fortunate enough that we do have a sales tax incentive for what we would say both, right? So this is exempting our sales tax on both state and local taxes. So the entire 7.25% for the county that I'm currently sitting in, we are experiencing a saving of $6,700. And a lot of times people might say, well, where are the grant or incentive programs for these types of projects? And too often this is overlooked, right? This is a real savings that if you're in Ohio, you're going to experience. So our installation cost is truly $1.85 per DC watt. Now in New York, it's a bit of a mixed bag. They have a statewide incentive for sales tax exemption, but it's at the state level. So if you look at, and I can't remember exactly which county I pulled in New York, but their 4% state sales tax was exempt, so they were going to have a sales tax savings there of $3,700. However, they still were going to pay their local sales tax, so this $4,300 and local sales tax was still going to be paid. So their allocation at the end of the day, they were at $1.92 per DC watt. So hopefully that helps kind of illustrate the impact of sales tax. And again, if you're not familiar with how your state addresses sales tax, I would encourage you to go to that Desire website and filter that for your specific state. Next, we're going to look a little bit at the impact of property taxes, and just kind of a real quick prereq on some terminology before we do is we think about property taxes. They're obviously addressed very differently depending on your local municipality and your state. But oftentimes we're looking at your nominal tax rate, or what's often referred to as a millage rate or a mill rate. That is essentially the number of tax dollars you're going to pay for every $1,000 of taxable value. And then that's going to vary significantly based on your county, township, school district, city, and so forth, so your local municipality. The assessment rate is going to be the percentage of the value for that property that is going to be subject to that tax. And your effective rate is simply going to be the product of the two. So looking at a small example here, you can see, I'm going to try again, stick with this same example just to try and, for simplicity purposes, keep these same numbers in our mind. So a 50 kW system we just showed earlier was $92,500 at $1.85 per DC watt. So in this example, I took a mill rate for a small business in the township that I'm sitting in here, and they were at 40.2. So again, that's the dollar value per the dollar amount of taxes paid for every $1,000 of value. So we would be paying $40.20 for every $1,000 of value. Now we can do some math and kind of convert that down or distill that down to 4.2%. So our mill rate is 4.2%, or our nominal tax rate, times our 35% assessment rate was going to give us an effective tax rate of 1.407. And if you applied that to our $92,000 system, you can see that we're going to pay right around $13,000 a year in additional property taxes if your system would be subject to that. Again, I think it was 36 states have some form of property tax exemption as it relates to renewable energy or solar energy projects. A couple of things that I would really encourage you, and this is based off of some conversations that I've had with farmers that have done this. At Farm Science Review, OSU has, we have an energy tent at the Farm Science Review every year, and we get farmers from all over the country that come through. I was talking with a farmer from the state of New York, and I mean, he was just thrilled with this system they installed. He was telling me all about the installation and how the technology works, and the different motor loads that he has that's powered with this system. And he installed a 9.7 kW system and was just thrilled with the way that the net metering was working. He could see his electric bills being lowered. But then he kind of got to the, however comment, and he said, one of the things that, really hurt him, and he said, as a result, he said, my system will probably, take longer than 20 years to pay back, was their property tax assessment. In New York, in the state of New York, they had a statewide exemption for renewable energy systems for property tax. However, that piece of legislation allows, or I guess offers your local municipalities, your counties and townships and villages, the ability to disallow the exemption. And so, in his proposal, it was kind of pointing to this statewide or state level property tax exemption. However, not being fully comfortable with the details or inner workings of that legislation, he didn't realize that his system was going to be subject to those taxes. So he said that his property taxes went up about $800 a year as a result of that system. And so that was just something they didn't account for in their cash flow table. So, the takeaway, the lesson learned there is I think twofold. Number one, policy is often complex. So just because you take and read a headline that, hey, there's an exemption, or it's not qualifying for this, you need to really understand the policy. And then also it's fluid. So there's just a constant churn of policy that's always evolving. And that's one of the reasons that John and I you'll hear us say this probably several times over the next 5 to 6 programs, is even the best modeling that we can do, there's still a certain element of risk in these types of projects. And a lot of that's due to the fluctuation of policy. And then the other thing is, it's worth an extra phone call to check with your local officials and really understand how they're going to assess the project. So send them an email or get something in writing that says, look, I'm considering this investment. The way I understand the policy, it should be exempt. Can you confirm that? And I think that's a simple step that could eliminate, some some disappointment that's due to a lack of communication. Insurance. Insurance is another one that, as you think about it, is going to be an ongoing cost you will occur. And so it's going to be something annually that you're most likely going to see an increase at some level that you should account for in your cash flow table or in your modeling. As a general guide, the National Renewable Energy Laboratory had a report. They were recommending just kind of off the cuff or back of the envelope calculation of 0.5% of your total capital investment annually would kind of be a good starting point. Now, I've kind of looked at that, and in some effects, I felt like maybe that was a little bit too much. And so I've done some modeling at 0.25% of the overall initial capital investment. And I was a little more comfortable with those numbers. But with that said, I recently spoke with a farmer that had a couple of finishing barns, and he was considering a project. And he's also in the insurance industry. He worked for a company and specialized in agricultural insurance. And he mentioned to me that for Class 1 coverage, a general rule of thumb for this type of a project, he would say, is $5 per $1,000 of coverage annually. And so again, if you would take that, 5 divided by your 1,000 and work that backwards, what do we get? It's basically 0.5%, right? So that kind of puts me back in. I think in general, if you want to model something, anything between 0.25% and 0.5% annually of the overall initial capital investment should give you a good benchmark. With that said, there's a number of factors. Is it a rooftop system? Is it a ground mount system? What's the size of the system? And so I think that at the end of the day, it really is upon the system owner or whoever's considering this to just make the phone call and see what does it cost to add it to their farm insurance. I've also had a couple of farmers say, I'm not going to insure them. My panels have good performance or production warranties that are built in. There's also a product warranty on the panels. It was a ground mount system. His comment to me was, unless there's a tornado or a fire, what could happen? And I guess if you're willing to roll the dice on that, that's your decision. But nonetheless, there's a couple different ways that we could handle that. I typically fall somewhere between 1/4% and 0.5% of the total capital investment. All right, so we're going to talk about kind of the operations and maintenance expenses at this point. And one of the things that we've done a lot of is we tend to focus on trying to put a dollar value based on the system size. And so again, we're focusing kind of in this bar here, this commercial system. And I've traditionally used $15 per kW for a lot of the modeling that I do. But John and I are always talking about how we can get better and how we can be more accurate in our modeling. And one of the things I'm starting to question is if we need to reevaluate how we're modeling this. And that's based on how much of that O&M is based on inverter replacement. And so we'll talk a little bit more about how we might do that better. But currently, $15 per kW annually, for a 50 kilowatt system, you can say we're looking at spreading out that cost over 25 years, $750 a year that we're allocating towards O&M. Not that you're going to use it every year, but accounting for it for if you do have a major component failure. Now, you can see the color coding there. The yellow, we're looking at cleaning and vegetation management, system inspection and monitoring, components replacement, module replacements. And so you might ask yourself, why do we need to clean these systems, or do we need to clean these systems? What type of inspection or component replacement might we see? This is a picture from the National Renewable Energy Lab report that is kind of illustrating why you may want to clean the panels. If you have, and honestly, the system John showed an image of up at Stone Laboratory in Gibraltar Island, we do have a lot of seagulls and birds up there. So we see some panels that look like this from time to time. This is an example of a system that was near a construction site. And based on the NREL report, they said that there was a 5% production loss based on when these panels were operating with this silt on the module versus after they cleaned it. So, I don't know, think about a ground mount system on your farm. If it's near a field and you're shelling corn or taking off soybeans, I mean, it might be worth going out to give them a good cleansing if there's not some rain in the forecast. But in general, most of our locations in the Midwest, we get enough precipitation that you're not going to need to really sweat over cleaning the modules. As we think about inspection and component replacement, there is some of that. Here's a couple of other examples where, and this is just an example of poor wire management. They had some snap ties and fasteners that broke to where it wore through the wire casing. But this is kind of sloppy work that probably could have been done a little bit better to begin with. Here you can't really see it, but we had a critter that chewed through the wires down here to where they had to replace some. And then on this cable tray, and this is on a larger system, but this cable tray had a couple of wires where the casings were actually sun-dried and were cracking. And then, of course, on the right here, you can see on the module, we had some water penetration. So this would be kind of an example of a panel defect or manufacturing defect. So point is, while these systems, for the most part, are very robust, there's very few moving parts. So from an operations and maintenance standpoint, solar tends to perform very well because there's not a lot of moving parts. There's not a lot of things that need replaced. But at the same point, if you're installing this system and you're planning for this to operate over the next 25 years plus, you're going to need to do some inspection, and there are some components over the years that will need either tightened, fixed, replaced, that type of thing. So we need to account something for operations and maintenance. So I mentioned earlier that we looked at how we model the O&M cost, and historically we've used, say, $15 per kW annually. One of the things that I'm questioning is if we could do that a little bit better. So given that inverters are such a large component of that O&M breakdown, maybe we reduce that $15 and say instead we apply $7 to $5 per kW annually. And then instead of kind of leveraging that larger cost over 25 years, we try and target when it's going to happen, and try and put in a lump sum for inverter replacement, or what maybe even more become more common is actual inverter coverage. So the reliability of inverters has really increased in recent years. I mean, I think 5-6 years ago, 10-year warranties were something that was really promoted, and now it's just kind of common practice that you're going to have a solid 10-year warranty with your inverter. And many of them now offer options for extensions up to 20 years on an extended warranty for that inverter. And so one way that we could look at more accurately modeling these types of systems is to say, okay, we're going to plan on $7 per kW annually as our annual operations and maintenance expense. And then in year 10 or year 15, when our manufacturer warranty is running out on that inverter, we'll plan on an additional cost that we're going to put in there to buy that warranty extension. Or maybe you just play worst case scenario and say, let's just, for modeling purposes, for project evaluation purposes, we just want to say we're going to have to replace the inverter on our 50 kW system in year 15. So maybe you model it at $5 per kW annually, and then in year 15 we can put in a one-time expense on this model to account for a $15,000 inverter replacement. And so just a way that we might rethink and a little bit more accurately evaluate these projects. And where that's really going to come into effect is when you think about looking at a payback period, a discounted payback period. As we discount future years of cash flows, adding that expense as close to the year when you're actually going to incur that expense is certainly going to be a more accurate project evaluation. Real quickly, I want to just touch on module efficiency and power. This is a chart that's looking at efficiency trends in the California market, which are similar nationwide. We're focused on this center line, which is looking at commercial systems. And in 2018, they were looking at an average of 19.1% module efficiency for commercial systems, giving us this average install cost of $1.82 per DC watt. And this chart showing if we could reduce or we could increase that module efficiency to 25% efficiency, we would reduce our cost to $1.64 per DC watt. If we could increase it to a 60% module efficiency, we'll reduce our cost to $1.36 per DC watt. Now, it is important to note that 60% efficiency for a silicon-based cell is not achievable. I think 33% efficiency is your maximum efficiency for a silicon-based solar cell. So, this would be a multi-junction cell, which is kind of that next generation. John talked about that a little bit last week. But essentially, we're showing that as we see efficiency increases, we'll see a corresponding downward trend in the installation cost. And it's also important to point out that a lot of the reductions that we've seen in installation costs to this point are reductions in equipment costs, as we pointed out earlier, and most of that's driven by either economies of scale or manufacturing efficiencies. So it's not like we've seen a major technological breakthrough in modules that has brought that cost down to this point. And then this is trending the module size in the California market over years. So you can see that we're seeing an increase in the size of modules, and this goes back to the spec sheet that John shared on Tuesday, when we talk about rating a panel. So a 287 watt panel. Mouse is not working. Here we go. A 287 watt panel. Can you still see my screen, John? It kind of froze for a minute.
Yes. Okay.
Okay, good. 287 watt panel. That's based on standard test conditions. So we're basing that on the absolute perfect conditions for for production, and John talked about how we would need to derate that for normal operating conditions, and this is from 2016. And actually, what I'm seeing more here in Ohio, and I think John would echo this for Nebraska, 300 watt, 315, 350 watt panels are even more common today. So if we had updated numbers, I would expect that we'd actually see a fairly significant jump for 17 and 18. So how does this impact the system cost? Thinking about moving forward, improvements in both the module size and the efficiency is going to reduce the overall number of panels or modules that you need to build a system. And so if you think about the impact of that, we're going to be reducing the amount of racking that we need, the amount of hardware, electrical components, and the amount of labor that it takes to actually to wire everything or configure everything. So as we continue to see or start to see larger increases in efficiency and power output from modules, we could expect to see a kind of an ongoing downward trend or a beneficial influence, I guess, on the overall system cost as a result of that. So lessons learned and additional resources as we kind of start to wrap up here. The one thing that I like to repeat is not all PV systems are created equal. Get multiple quotes. As if you learn nothing else from the session, then get multiple quotes, because it will help you identify quickly if something is way out of line. The other thing that I think is important is to make the installer sell you the system. And good installers love to do this. They love to tell you about how they've designed their systems and the equipment and the components that they're using. Have them tell you why their product's the best. Too many times I'll ask, I can think specifically to one conversation where we were looking at 4 different proposals. And I said, well, what's the difference in these systems? And the response was, well, nothing. They're all 40 kilowatt systems. And, so under that logic, I would say, well, these 2 cars are the same, right? There's no difference. They're both 1968 Fords, 2-door vehicles with 4 wheels. So, but the reality is, they're very different. So we need to think about the design, the equipment, the components, the performance of that system. And so try to train yourself, if you're a farmer evaluating this, or if you're working with farmers, encourage them to really think about, answering this question: why is this product better than the other? And part of that may be to the design. Maybe it's a ground mount versus a rooftop in terms of optimizing the production. Part of it could be based on the warranties that we've talked about, whether it's modules or inverters. I'm going to kind of real quickly show a chart of modules and warranties. And this is kind of busy, but I'll walk you through it. There's really 2 different types of warranties associated with solar modules. And part of that is a production warranty. I've just had someone else join the call. I had to let them in the room. Part of that may be a production warranty. And so here we're looking at the green bars, and this is measured in terms of years. So how many years is the product warranted from a production standpoint? So think about, manufacturing defects that may occur with that product. Whereas on the right, we're looking at our performance warranty. So, and this is where, kind of as an industry standard, and John talked about this Tuesday, 80% of what it was out of the box after 25 years is kind of a good industry average. And you can see most of these yellow bars, kind of meet that 80% of what it was producing year 1. It's going to produce 80% of that after 25 years. However, there are some panels that are, peak performers, and you can see up to 90 to 92% of the performance in year 25 as what it was out of the box. So, again, back to the idea of, are all systems created equal? It's certainly worth kind of digging into the details of how those components, what components they're using and how they're warranted, and what type of equipment they're using. Same things for the inverters. When we think about installation or workmanship warranties, what does that look like from one proposal to the other? Fastener types. I'm aware of a couple installers in Ohio. If they're doing rooftop systems, it's no questions asked. It's not even an option. You only get stainless steel fasteners. I'm aware of others that will put galvanized up, and so there's certainly a difference there. And wire management, roof warranties. If it's a rooftop, will they warranty that against leaks? So certainly, really kind of dissect the projects. Don't just assume that because they're the same size system that they're all the same. Another example why we would want to evaluate multiple proposals, and again, this was a real-life example. We had a 100 kilowatt system in Ohio that was being looked at, and they had 3 proposals. This is the metric that's always kind of held the highest. It's the payback period. Again, we'll talk in in session number 5, why payback period, while it has some value, is certainly not the only metric that we would want to look at for evaluating these projects. And then we can kind of look at energy savings over 25 years. As I look at these numbers, I can almost guess what type of an energy escalation rate we're using or working with here in project number 1. And ultimately, I can tell you it was 10% energy escalation for 10 years. Whereas this one, I think, was at 2.5% energy escalation rate. And so, the one thing as we think about evaluating these, we can tell any story we want to tell if we're willing to sacrifice our integrity as we select numbers. We need to do our best, our best to the best of our ability, be accurate with what we're projecting. Right? Modeling is nothing more than trying to predict the future with the best information we have. And so, is 10% energy escalation likely? Based on what we've seen in the past, no. And this is another, again, pet peeve of mine. Often we see systems reported in this net system cost, right? So it's, okay, you can put a 100 kilowatt system in for $41,900. And that's just not true. What this is this is looking at the system cost after the value of your 30% investment tax credit is removed, after you've monetized depreciation, maybe a REAP grant, the value of SRECs. And so, at the end of the day, you're still writing a check for the gross amount, right? And for proposal 1, you're not writing a check for $41,000. You're writing a check for $425,000. So one of the things, and because this number, since the net number is very often shared in these proposals, sometimes you might have to ask, well, what is the cost before all these incentives? Because it's not always clear. But once you have both numbers, as we start to identify this gap, it's very simple. The larger the price gap between your gross and net system cost, the more aggressive your assumptions are. And then to kind of tell the rest of the story or put a ribbon on these examples here, if you really break down the installed cost per DC watt based on their gross system cost, we're comparing now $4.25 per DC watt for proposal 1 versus $1.86 per DC watt for proposal 3. And long story short, I can say that this farmer did select proposal number 3, and it's been installed and operating very well for 2 years now. Kind of the last couple slides on lessons learned. Focus on the number you have to put on the check, and that seems too simple, but it's often overlooked. Identify the differences in systems, so really understand the product you're buying and what components are used, what design is going into that makes it different from another system. Compare your manufacturer's warranties, and then ask for other farms they've worked with. Take the time to either make a phone call or hop on your vehicle and cruise on over and take a tour. And then finally, often I feel like, I'm going to say, to back up, there's nothing cooler than when I'm on a farm where we've had a system that's been installed and you can see all these ventilation fans running and feed auger motors and well pumps, and you know that it's powered with the sun. It's a really cool feeling to be there when that's happening and see that. But with that said, there's a lot of considerations that go into whether a system makes economical sense for a farm or not. And so while I don't want to feel like we're trying to kind of nitpick proposals and kind of pull out all these little nuances that need to be considered, individually, yeah, they're not a big deal. But when you look at these all in aggregate, it can make a very big difference in whether a proposal has a positive financial analysis or if it's one that you look at and say, I should probably invest my money elsewhere in this business. I think we have about 5 minutes, John. So maybe what we can do is take some questions. I'll put the closing poll up. And then once we wrap up at 1:30, if anyone wants to stick around for like 5 minutes, I would open up the system advisor model. Again, we're going to have an hour on this on session 6 where we really get into the modeling. But just to spend 5 minutes and kind of introduce you to that model, maybe we could do that after 1:30 if anyone's interested. So at this point, John, I will go ahead and put the poll up and then take some questions.
If you have any questions for Eric, let's go ahead and type those in the chat box now. The other thing I would suggest is, you know, if we can take turns, go ahead and just unmute yourself and ask the question, and we will take questions by voice as well. As we're waiting for some questions to come in, we thank you all for joining us. We will have this recording up and sent to you by tomorrow. If you have to miss sessions, just remember that we will be recording these and you'll be able to review them. And we would love to, you know, we're here to help get you information. And so if you, you know, want to run a model of a system, you can always feel free to contact Eric or I, or we can walk you through that on a personal basis as well, rather than just this group session. So we are willing to help people that need that extra detail. So glad you're able to join us. Let's finish up with a few questions.
And I'm going to go ahead and close the poll now, John, and I will get ready to open up the SAM model while, you know, if there are questions that roll in, and then if not, we can just give them a real quick snapshot of what that tool looks like.
I'd say go ahead and open it up. We have quite a few people staying on. I haven't heard any questions yet. So we're going to give an introduction very briefly to the system advisor model. And when I say a brief introduction, we're really going to focus on the system costs portion of that today. But this will help you at least get what does it look like. And we're going to cover this in week 6 in greater detail. Okay, so I have the model up. Can you see it, John?
I can. So again, this is a free download. The link is in the slide deck that is in the video. We'll share with you. You can also just Google System Advisor Model or NREL SAM. It comes up. Or just email John and I. We can send you a direct link. John, you could even put it in the chat box now. But basically, once you download this tool and open it up, you can start a new project. And the one that we'll encourage you to use until you get comfortable with this is the PV Watts version. Now, this is different from the PV Watts that you might find that just does the production. This also includes the financials. So we'll select a commercial distributed system and hit OK. So is that large enough that you can see it on your screen, John?
Okay. It's a little small, but it's okay.
I can try and increase it. Let me know if it
Just
works.
Keep going. It's all right.
Okay. So from this page, you know, we'll have the ability to plug in our weather data, and we'll get into that in week 6. And then we can kind of go through our system design, losses, a number of different details. System cost is where we're going to look at for what we kind of played with today. And you can see this itemizes our system cost very similar to what we looked at. So it has a cost for modules, a cost for inverters, your balance of systems, labor, overhead, contingency, permitting. You can get very detailed in how you want to build your cost. One of the things that is helpful for me, because most of the proposals that I see that farmers are looking at is not itemized like this. They just have an overall cost. So I tend to go through and zero out all of these costs and then base the system cost off of what is our installation cost per DC watt based on the gross system cost. So just what we were talking about. So you can see now our total installed cost is 0. So I can just come up here after I have everything zeroed for modules, and let's just say we're going to put it in right at $1.80 per DC watt. We can plug that in, it'll calculate it, and you can see this is at $1.93 per DC watt. What that's telling me is we do have sales tax turned on. If we went here and swapped that sales tax out to 0 on our financials page and then went back to system cost, now we're at $1.87 per DC watt. So our contingency was still built in there. If we zero that out, now we're at $1.80 per DC watt. It really helps to do accurate modeling, at least in my opinion, if we can kind of zero everything out, start at kind of a square one to really understand what are the impacts of the numbers that we're putting in and make sure that we're understanding how these are being calculated. Where I could see the value in all these itemized cost items is for someone that is putting together a utility scale system. So in some examples, developers will use this tool to put together a project that they may be selling or proposing to someone. And in that instance, this would be very helpful. But for looking at it from a farmer's perspective, we can kind of do just the system cost. And then the last thing I'll point out is we mentioned operations and maintenance. So at the bottom down here, this is $13 per year, $13 per kilowatt per year. We have the ability to do escalation above and beyond inflation for that. So if we think we're going to have higher O&M costs towards the end, maybe we start this at $5 per kW annually with a 1% escalation. And then we could even come in and so we could do that, put it 5% annually. And so we want a 1% escalation on that. Then we could do a fixed cost where we come in and edit this. And if we wanted to go to year 15 and say it's a 50 kilowatt system, we said it was going to be $15,000 to replace that. We can plug in that one-time cost right there. And so a number of different ways that we can handle that O&M. I guess the last thing that we did talk about, in addition to the sales tax, which is there, would be insurance and property tax, and those are both addressed on the financials page. So we right now have that set at 0.5% of the total installed cost. So that's really all I wanted to share now, unless someone has additional questions as it relates to SAM. But this is something that we're going to spend a lot of time in on session 6, and I just wanted to kind of give you a snapshot and make you familiar with, as it relates to today's materials, where that information fits into the modeling. So
the advice I'll give about SAM is that it at times it has a lot of power because it has a lot of ability to change parameters, but that also makes it a little bit overwhelming. So if you get a little overwhelmed with it when you start with it, just take a deep breath, ask some questions, and we can help you try to get some of the things said if you want, because it can, because of its ability to manipulate it, it also, you can actually make some, there can be some issues in there and get numbers that aren't very valid. So the other thing is that when you download it, it's going to ask you for an email, and then they're going to email you a PIN number or a key number that you'll put in. And then every time you log in, basically it has a counter that counts how many people log into it. And basically the people at NREL have told us that they use that to monitor its use so that they can get more grants to maintain it. That's what that's for. It is free, but they do just monitor how much it's used just so that they can keep up maintaining it. So,
and I think, John, your point, and I don't want to overlook it, your point that it can be overwhelming and contact us is an important one. I mean, John and I have spent, I don't know, the last 4 years now kind of pushing each other on how to learn more about this tool. And one of the things that we do is, we'll have face-to-face programs with farmers in Ohio on, solar financial analysis. And we might have a room full of 30 or 40 people. And from that, I might get 1 or 2 phone calls the next week. And they'll say, I want to know more about the modeling. And what we do is I tend to encourage them to download it and start, just to get them to play with that. They can save it. And then normally what we'll do is actually help them refine that model and help them understand the impacts of these different changes that we're making. But based on how we're doing this program right now and the ability to meet virtually over our computers and look at the same information, John and I can help a farm real quickly go through some modeling and kind of optimize their SAM model. And we're certainly willing to work with those of you on the call here as well today.
Very good. Everyone have a great weekend, and hopefully we'll see you next Tuesday.
Thank you.
Very good, Eric. I think that went very well.
Yeah, I was just reading through some of the notes in the chat box to see what I missed.
It was mostly me. There wasn't a lot of questions.
That's good. Kind of putting clarifying points out there. I mean, the safety one for first responders is a big one.
Yep. Well, and it's one of those things where you think that the 2017 electric code, well, everything's that way, but we don't go back and fix old ones that were applied appropriately under previous electric codes.
Yeah.
So,
and we have a fact sheet here that we put out at any of our programs just for that point.
Good. And that's kind of what I emphasized with respect to the lineman that I talked to. Now, interestingly, my installer friend said that you have this disconnect, right? That's there for theoretically, people to use, right? But
yeah.
A general lineman is not actually legal to use it. A first responder, I suppose, might be able to, but a lineman, they are not supposed to be able to touch anything on the customer side of the meter unless they're a licensed electrician, with certain rights. And so, if they just come out and they're a lineman, they're not supposed to flip that.
Yeah.
So that's a real interesting piece of the electric code that says, oh, that's on the customer side of the meter.
Yeah.
Now, maybe the contract that you sign has some information in it that says that they can, but I don't know. It's not that. He says, here's this disconnect we're putting in, but they're really not allowed to use it.
Yeah.
So
what overall, what are your thoughts on the slides?
Honestly, I think we've talked about that. It gets better every time, and I think that you did it really well, and I really liked how you went piece by piece with the percentages through that start.
Yeah,
that was really good, and then also had the historical context of each one. I know you did that before, but the way you did it this time made it really clear, and so it was really good.
Yeah, I just felt like the slides last time, I mean, you can get all that information onto those slides with a primary and secondary axis, but it just gets clumsy to follow.
Yep.
And so I kind of thought, well, at the end of the day, we're really interested in what percentage of that overall cost is accounted for in 2018, right? So, that to me, I thought that was, in my mind, it would have made it easier to absorb. So I think, or I hope it did. But good. Anything, I guess, looking ahead to Tuesday that we need to?
Not yet. I'm gonna, review my slides and get them all set. I think they're pretty close, but I want to get through them a couple more times, and then I'll let you know if I need anything.
Okay, great. Sounds good.
Thanks, Eric.
Hey, thank you. We'll talk to you this week.
Have a good day.
Yep, you too. Bye.
Bye.